All right, I guess I am live. Hey everyone, I am Ashish. Welcome to the AI Bootcamp. So today finally is the day. So let's get started with machine learning. Our agenda to study machine learning wouldn't be like going deep into mathematics or like going deep into the coding part. We just want to understand the basics of it. That's it. And basics as in intuition. And we just want to, I want you to just be prepared with the basic machine learning so that in future, if you see a heavy kind of code, you would be able to figure it out on your own. Okay, what this code is doing. So first of all, there are three types in machine learning: supervised, unsupervised, and reinforcement. What we are going to be focusing on is first two, which is supervised and unsupervised. Supervised learning means that there is a supervisor, or you can say that there are in the data set, there are some features and some answers. There are some questions and some answers. We're going to feed question and answers to the algorithm, to the model, and what basically would happen is the model would try to map the questions to the answers. So in a way, the training happens. Let's actually look at what the model is. I mean, I keep using the word model, but I never told you what the model is. So first of all, a couple imports. I'm selecting the data science environment. Let's say you have the basic data set, something like this, where you have work experience of 1 to 3 years and salary of 1,000, 2,000, 3,000, and this is in dollars. So a question would be the feature set of work experience. The answer would be salary. So you could say work experience determines someone's salary. So the question is work experience, answer is salary. We're going to feed the entire data to the machine, but in two parts. In one part there would be the questions, in the second part there would be the salary, I mean, which is the answer. So in this case, right now, if I were to ask you a simple question like if the work experience is 4 years, then what do you think would be the expected salary? And one 1,000, 2,000, 3,000. So I guess you can see the big picture. 4,000, it's to be expected. Our human brains expected a pattern like this. So we imagined that there is a line passing through these three data points, and this line also crosses 4,000. So 1,000, this data point 2,000, 3,000, and then 4,000, 5,000, and so on. Now, point being, okay, as a human, I can imagine this kind of pattern, but how does machines identify the pattern? So, one way to look at it would be that you could try if else. If work experience is 1, then salary is 1,000. If work experience is 2, then salary is 2,000. But then, how many if statements can you make? Probably 10, probably 100. That's a rule-based approach. But what about 1.1? What about 1.11? What about 1.001? Basically, all the continuous range. What about that? There are infinite numbers, right? Between even 1 to 10, there are infinite decimal numbers. So, a better approach would be saying something like salary equals 1,000 times work experience, isn't it? So, salary is 1,000 times work experience. And if I write something like plus zero, that wouldn't harm us in any way, right? So the entire equation should become something like this: salary, or if you remember your high school mathematics, there was an equation of y equals mx plus c. That's a line equation. And that's regression in a nutshell. And regression is the basic machine learning algorithm. So, and this is the basic unit of a neural network, which is called a neuron. And yeah, you might be thinking right now, like, this is such a basic stuff, and how can it be deep learning, machine learning? How can it be, machine learning, this simple equation? And it is because machine learning is nothing but your mathematical logic. It's not intelligence in any way at all. It's just the way you define the logic. Model is just the mathematical equation. Model is fed data. So take a look. Salary equals 1,000 time work experience. Work experience and salary. These are the data where work experience determines your salary. So work experience is the feature set. Salary is your independent column or something to predict. So we are going to predict salary with respect to work experience. You increase work experience, salary increase. You decrease work experience, salary decreases. And what about this plus zero? I'm writing this plus zero to mimic this kind of line equation. And if I plot this line equation onto a map, this is how the line equation look like. But machines don't exactly come to this pattern on the first try as we humans do. Like we could see the data. This data is very short, so we could see the data and identify the pattern. Okay, 1,000, 2,000, 3,000, 4,000. So we can, as a human, imagine outright like 4,000, 5,000. But machines would be doing a different job in the back end. What machines would be doing is, first of all, machines would be writing this entire equation in something like this form: salary equals work experience times some number m plus and some number c, where m and c could be anything. M and c are just some values, could be anything at all really. So let's say in the first iteration, the m value and the c value is 1 and 1. Or let's say, let's take it 1,000 and 1,000. So salary becomes, what I mean to say is, let's take the value of m as 1,000 and take the value of c as 1,000. So in this particular model, in this model right here that we have, this is my model 1. This is my model 1. This is the logic that I defined for model 1, first model. In this model, if I put work experience as 1, I'm getting 1,000 plus 1,000 salary as 2,000. Yes, it's wrong, but it's very close. Take a look. If work experience is, if I were to plot a picture, if work experience is 1, then the salary is 2,000. If work experience is 2, then salary is 3,000. Am I right? 2, 2 plus 3, 3,000. Yeah. So the point is 1, 2,000, 2, 3,000, 4, 5,000. That's the sort of data we have. And now the model is making some error. Now, how to decrease that error? That comes in the next part, which is gradient descent, but we are not gonna go into what gradient descent does, because this is not a mathematical heavy tutorial. So point being, like let's say I'm writing the equation as y equals ax plus b. I'm just I can write it as mx plus c ax plus b, or in machine learning lingo it is called theta 0 x 0 plus theta 1 x1, because this is a matrix form. So it's written in a matrix. And if you don't know what matrices are, and if you don't know what linear transformation of matrices are, still fine, because our agenda is not to discuss mathematics. Our agenda is to discuss intuition. So my point being, there is some measure in which error is being calculated. And now let's just take a look at, like, this is the optimal model in which m and c values are 1,000 and 0 respectively. But your machines wouldn't start this way. Machines would take a random guess first of all, and in the first random guess, let's say the value of a and b are 0 0, which is value of m and c are 0 0. Then the entire equation becomes y equals 0. And if you were to plot y equals 0, you would get this black line, meaning no matter the work experience, your salary is 0, right? So basically, I'm saying salary equals 0. No matter the work experience, salary is 0. That's what this line is depicting right now. But this isn't really much useful. But in a case to study it, let's just calculate how much the error is. So for the point 1, as we can see over here, the prediction is 0. For the point 2, the prediction is 0. For the point 3, the prediction is again 0. But the actual values are 1,000, 2,000, and 3,000. So if you are to calculate the total error, that would be 1,000, for this one, this yellow line for 1000, 2000 for this yellow line, 3000 for this yellow line. And as a good practice, we take squares of error because let's say if you have positive and negative differences between these, so positives will cancel out the negatives. So we will take a look at what I'm talking about in the positive will cancel out the negative uh, uh, part. So basically, what you can at the moment think about is that the error equation is that over here, the error equation is 1 upon 2m. This sign is for summation. Summation of predicted value minus actual or actual minus predicted to the whole square. So let's calculate it first to get a gist of it. There are three training examples, meaning there are three rows. There are three data points that I have to calculate for the error, right? So 1 over 2 multiplied by 3. 1 over 2 I'm taking because I'm gonna take the square. So I'm gonna take the error square. So that's why I'm just taking 1 over 2, because if I'm to go a little bit technical, then it's something like this. If you take differentiation of a square, if you take x square differentiation, that becomes 2x. So 2x multiplied by 1 by 2. So the 2 and 2 cancels out. So that's why in a mathematical lingo, we take 1 by 2, but it's really not necessary. If you don't want to take 1 by 2, don't take it. Wouldn't hurt. This 1 by 3 is to average out the error ratio, not a ratio, but average out the errors. So take a look. In this case, the first error is 1000 and 1000 square will become the first error square. The second error is 2000. So the second error square would become 2000 square. The third error is 3000. So the third error square will become 3000. So that's what we are doing over here. Prediction 0 minus 1000 to the whole square. 0 minus 2000, which is second prediction minus second actual value to the whole square. Prediction 3 minus actual 3, 0 minus 3000 to the whole square. So it becomes something like this. So the total error is coming out to be 2 triple three triple three, which is, I don't know if it is high or if it is low. There is no comparison matrix right now in front of me. If that would say like this error is high, a, a error of 2 million really means nothing if I don't have anything to compare it with. So in the next iteration, what I do is I try to change the hyperparameter values. These not the hyperparameter values. These are the trainable parameters. We will talk about what parameters are trainable or hyperparameters, but this is a mistake. This is not a hyperparameter. This is trainable parameter. Okay. Anyway, right now I'm choosing the equation as y equals 2000x. So what I'm saying is initially I chose a and b as 0, 0 random points. Now in the second step, I'm again choosing random points 2000 and 0. So let's calculate the error now. Now my line shot up quite far away. So the predictions are more than the actual values, right? So now if I calculate the entire error, then see the error is the same, even though the hyperparameters are different. But I still don't know if the error is high or if the error can be minimized further. So let's take a look at the third case. In this case, I'm taking the value of A as 500 and B as 0. I'm intentionally keeping the value as 0 to simplify some things so that I only change the parameter A. So if I take y equals 500x equation, the line is something like this. And the mathematical error at this point becomes first prediction minus first actual value, 500 minus 1000 to the whole square, 1000 minus 2000 to the whole square, and so on, so on, so on. You would see that the error is 500,000, which is lesser than before. So definitely this particular model is doing better. This particular mathematical equation of y equals 500x is doing better than the previous equation, right? Take a note of that. Now I take A as 1500, B as 0, and repeat the entire process again. And now the line shot up. but the error still remains the same 500,000. So now I take y equals to 50x and then again calculate the error. Now my error got increased to above 1 million. So the point is, in the entire process, I would uh, keep noting out where the what the values of A are, what the error values are. So take a look over here. I'm saying the lowest error 0 happens when the value of A is 1000, and I'm keeping the value of B constant for a reason so that things become a little easy to visualize. And now if I plot this thing, then you would come across something like this, which means that really at the value of trainable parameter A, it's not hyperparameter, it's trainable parameter. At the value of trainable parameter A equals 1000, the error is lowest. This MSE mean square error, because we were taking square and then we were taking the mean of it. So error squared, then mean. So MSE, mean square error. And because it's a square, so of course it's a parabola upwards, or what does it call? What is it called? Concave upwards kind of a shape. So the point is, as you move away from the optimal value of trainable parameters, your model starts to make errors. So uh, after the initial guess, the machines would take initial guess, and that is most likely 99.99% likely to be incorrect all the time. So our objective becomes to decrease the error. So we train the model in a sense that we improvise on the model using the data set. So the algorithm in the backend that works for it is gradient descent. You don't have to go into the details. I'm not going into the details of gradient descent, at least not now. So you could see that eventually you would come across a value of trainable parameter where the error is lowest. And that's where the model performs the best. All right. So let's take a look at this entire process in scikit-learn way. So the data frame is df1, I believe. So what I'm doing is take data frame one, work experience, dot values means take the numpy array out of it. I mean, take the numpy array for it. Like, let me show you. Dot values just converted it to a numpy array rather than series. X dot reshape X would mean that convert this entire thing into as many rows but one column. Minus one means as many rows, and over here one means just one column, because we need it to be a column structure, because it needs to be a 2D shape. And why is that so? Because we have, let's say, work experience, we could have multiple features predicting salary, number of projects. For example, we could have work experience, number of projects, uh, and number of leaves an employee takes. So that could also determine their salary. So the data which is used to predict the salary is in form of a 2D shape. That's why it's a standard to take the X part in a 2D shape. So instead of taking one list line bracket, we take two list line bracket. So we are separating the data into one column for work experience, one column for salary. So we are saying that we will take X as work experience and we will use the X to predict Y, which would be the salary. Again, let me repeat. We will take X to predict Y. We will take work experience to predict the salary. And this is simple linear regression, where we take just one column to predict another thing. We take something like a feature or an attribute of a data set, you could say. We take a feature and we use that feature to predict output. So as a Y, I'm taking the salary column. So salary column becomes 1000, 2000, 3000. And as you might have noticed, salary need not be 2D in nature, because salary is just one single I mean, feature set could be more, one feature, two feature, three feature, but the thing that we want to predict is one only, which is salary column. So that's why it needs to be only 1D. So after we have taken the data set, after splitting the data set into features and the output, which is the X and the Y, we will use X to predict Y. So over here, let me show you first of all. the best way to remember this kind of syntax is sklearn, and I'm gonna use something like linear regression. The documentation very beautiful for linear regression. You scroll down, you would see the entire code right here. You could just copy paste it. Import numpy as np. This is the statement from sklearn.linear model. Import linear regression, and over there you would see the usage as well. So you don't need to like hardcore remember all the stuff. But over here, take a look. I'm importing the statement for the linear regression class. I'm gonna use the word function at the moment. I'm using the function linear regression. I'm importing it. Then I'm saying make an instance of this object. Let me repeat. Linear regression, something I import. I don't care what this something is. It could be any object. And I'm creating one object out of it. So of course, if I'm creating an object out of it, and I know that this requires brackets, so it's a class, and this is an object. So it has two important methods: fit and predict. Fit means look at the data, take a look at X, which are the questions, take a look at Y, which are the outputs. Take a look at X, then take a look at Y, map them together, and learn the pattern between them. And that's the pattern which we call a model. And then reg.predict 4 should give you 4,000. Reg.predict 5 will give you 5,000, and so on. Pretty simple, right? Mm, all right. So that was the, I would say, basic of linear regression. And let's not get into gradient descent just yet. So it's only these three, four lines that are important really. We won't be diving deep into like what's the mathematics behind everything, but we'll do a little bit of coding at least. All right, I'll see you in the next video. In that next video, we will be taking a look at the housing datasets where we will do multiple linear regression and compare multiple models as well, like how we will take the features to predict the outcome. Right? I'll see you in the next video then.